The following presentation is furnished by Hack. This is a presentation for Project 20, also known as the small-scale Android-docked telepresence robot.
Hey, I'm Hainam.
I'm Adam.
And I'm Kris.
And we are
Hack.
Here we have highlighted an outline for the Project 20 presentation.
First, we will begin with an introduction to our project, including a project overview and the motivation behind our project. Second, we will discuss the engineering requirements set forth for the telepresence robot.
Third, we will give an overview of our system block diagram and our essential subblocks within it. Fourth, we will cover the unique design constraints and impact on the overall approach to the project.
Fifth, we will cover a timeline for future work, and finally, we will conclude with a project outlook.
We begin with an introduction to the telepresence robot project. We have a set of 4 defining goals for the telepresence robot. First, the robot must be portable and small. This means that the robot must be easy to carry with only one hand.
The robot itself will weigh less than 3 pounds. It will fit inside a 1 cubic foot box.
Second, the robot must be inexpensive to the end user. This means that the robot needs to be manufactured using the most cost-effective components possible.
The telepresence robot should be able to be constructed for less than $150. The end user will see the benefit of inexpensive construction for a low final price. Our main competitor in this class of product is selling theirs for over $250.
Third, the robot must be equipped with the features that are desired by the end user.
The software included with telepresence robot will provide a simple user interface in which the controller device, namely a remote user, to interact with the controlled robot. Features such as the ability to tilt the docked Android phone and control the robot's overall speed across flat surfaces will be implemented.
Fourth, the robot must use a docked Android-powered smartphone or tablet. This means that the robot must be able to connect to the docked Android device in order to facilitate communication of the motor control signals and other essential status information.
The final telepresence robot should be compatible with Android devices operating on Android operating system versions 2.1 Eclair through 4.1 Jelly Bean.
And lastly, the Android phone or tablet must be able to make video calls to another Android-powered device using our software.
Now we will focus on the 5 major block groupings for our design. The major functions of the power supply block are charging a battery pack and regulating voltage from a battery pack to power the robot. This means that there will be 2 subblocks, a battery charger subblock and a voltage regulator subblock. The battery charger subblock will take power input from either a 12-volt DC power adapter, which will be plugged into a US power outlet supplying 1 amp, or a USB port which provides 5 volts supplying 500 to 900 milliamps. The voltage regulator subblock will supply power from the battery pack to feed other blocks that make up the robot. To the best of our knowledge, we will need at least 2 different power rails coming off the voltage regulator subblock to the other blocks in the robot. The motor operation block will include the motor driver and the motors. It will take the signals from the output pins on the microcontroller and send the proper amplified, pulse width modulated signals to the motors. The signals that are sent to the motors control the speed and direction that the motors operate in.
The audio input and output blocks will handle the audio signals coming into and out of the hardware. There will be 2 of these blocks, one on the controller side and one on the controlled side. Additional hardware will not be required on the controller side, as Android devices come with a microphone and speaker built into the hardware. This means that only some code will be required to implement the audio input and output block on the controller side. On the other hand, on the controlled side, both hardware and software will be implemented. The software for the audio input and output blocks on both the controller and the controlled side devices will have similar functionality. The microphones on both sides will pick up the environmental sound on the respective sides. filter out unwanted noise through a preamplifier, and send it to the other device wirelessly. Once the audio data is received, the data will become output data and be sent to the speaker system on the respective side. The output data for the robot will be traveling from the controlled device through Bluetooth to the microcontroller. The microcontroller will then push the data through a digital to analog converter, or a DAC, and followed by a Class D audio power amplifier before finally reaching the speaker.
The microcontroller block will be a single chip. The chip will process the data sent to its input pins and output ports. This means it will need to take all the input signals that are received and then decide which signals to send out to the various output ports that are attached to it. A microcontroller code block is required for the microcontroller to operate. The microcontroller code block will include code that processes the information received from the microcontroller's peripherals. The microcontroller will then output the needed information for the rest of the robot to function. It will do this by decoding information sent through the Bluetooth and then determining the correct signals to send to the output pins. The Android code block will use code developed for video calls overlaid with code that will be used to send and receive data. The two different devices will have one of two modes, one being the controlled, which is the device on the robot, and the other being the controller, which is the device that remotely controls the robot.
Let's look into the design constraints that make our project unique.
Our design has 5 constraints. Each of these constraints will influence an aspect of the final design. We want the remote user to have precise control over the robot. Because of this constraint, and because we feel we need an open-loop system for motor control, we have elected to use stepper motors. The stepper motors in our design will use pulse width modulation to rotate the motor shaft in exact increments. By controlling the modulation through the GUI, the remote user will be able to drive the robot around any flat surface, including meeting room tables. Binaural sound, created through a precisely spaced microphone array, will allow remote users to hear the environment that the robot is in as if they were actually there. This feature will be active whenever the remote user has headphones plugged into their Android device.
Having Bluetooth connectivity means there will not be any wires needed to connect the Android device to the robot. However, this will require either additional hardware in the form of a Bluetooth controller or a microcontroller with Bluetooth built in. We have chosen a microcontroller with built-in Bluetooth for simplicity. To maximize the number of devices that will be able to use our product, we have decided to use a microcontroller that supports the latest Bluetooth version, namely 4.0, as well as maintaining backwards compatibility with devices supporting Bluetooth profiles 2.1 and 3.0 high-speed. With Android OS being the platform of our software development, we will need to take the various versions of the operating system into consideration. As stated prior, we will support Android OS from Eclair through Jelly Bean. We will also need to take into account the various form factors of many Android phones. A scalable graphical user interface will be implemented for this last consideration. Setting a limit of the bill of materials will force us to use inexpensive products that are robust. Most of the components we have selected for testing are within Texas Instruments' catalog of devices. We plan to use at least 3 components from TI within our design, since we have elected to participate in the TI Analog Design Challenge. Now that we have a good idea of the final product's requirements, block diagram, and design constraints, the next step is to design and build each of the blocks in the block diagram.
Week 11 through 13 will be spent ordering and receiving components and parts of the major blocks. During this time, the prototype of the graphical user interface for the controlling side will be developed.
Weeks 14 through 15 will be spent implementing each of the circuit blocks. Weeks 16 through 17 will be spent completing the code blocks.
Week 18 through 19 will be spent integrating the hardware with the software and debugging. By the end of week 20, we will finish the construction of the final product.
This has been a Hack production.